Hey, I'm back, AP Calc. The thing shorted out on me and stopped working in the middle of my recording, so I'm just picking up right where I left off. Now, I think we should use the integral version to find k of 30. That's the key. So we're going to open up our calculator, open up fn_int in alpha 4. I'm going to make this bigger. Right there. We're doing the integral from 0 to 30 of our original function, 8 minus cosine of x plus 0.01 x squared plus 0.01 x, all times dx. This is going to give us the total amount of electricity used over this period, 335.488 megawatts, I think is the unit on this one, so we'll call it good. 0.488 megawatts. Like that. That'll be your answer for part B. You would get the same thing if you plugged in 30 into this function also. You'll have to trust me on that one if you want to. It's up to you. But I like the integral function better because it helps to solidify the connection between the rate function, lowercase k of t, and its accumulation as an integral. That's a much more important connection. Question C asks us to use our calculator to examine the graph of k of t on this 30-day period and calculate the average amount of electricity used during this period, during this month. Does your answer match what we got in 144, and how is the rate represented geometrically on this graph? Well, we did this problem today in class. We found the average, and it was, I think, 11.183. That is the rate that we're looking for. 11.183 is the answer that we're searching for. I'm being very careful not to short out my tablet here. So we are looking for an average of 11.183. During class, we did this with the integral version, but today we're going to do it using the derivative version. So I actually have this already prepared over on my other monitor. I'm going to pull it up to the front here so you can see what I'm talking about. I did this all in Desmos, and I recommend that you use Desmos for this because I tried it on my calculator also, and it took forever. It took my calculator a long time to graph this. So you'll notice that a couple things. I'm just going to actually get rid of this stuff first of all. Here is the original function, or at least the integral function. Now, all I did was type into Desmos exactly what I had before. I typed in the original function. You'll see there is the original lowercase k of t that was given to us. And I put it inside of an integral going from 0 to x. And I think that's the way you should do this. You could type in the other version of it if you wanted to. Our expression was capital, I guess I could do some other f of x equals. We had 8x minus the sine of x plus 0.01 x to the third power divided by 3 plus 0.01 x to the second power divided by 2. We had that same function. Oh, that's right. This is the antiderivative function. This is not the same thing anyway. I'm making sure I got this typed in correctly here. I'm going to leave that up there because I think those are both correct. I think the red one is the original graph, and the black one might be some sort of derivative that I got. I think I got this right. I'm just going to double check this really quick against something else in my notes. Doesn't matter anyway. I'm going to turn this black one off for now. Now the average, which actually I'm going to flip back over to my tablet for a moment to calculate because I think that's important that we do. I'm going to bring this to the top. Make this a little smaller too if I can. Good. And then I'm going to bring me up too. Webcam. Hello. Now, if we're going to do the average using the derivative version, what we need is we need capital K of 30 minus capital K of 0 over 30 minus 0. Now, what's nice is that we've already done most of the work for this problem. Like, we already did K of 30 in part B, 335.488. I know that K of 0 is 0, and this is all divided by 30. And so, the average that we get, 335.488 divided by 30, is, bada bing, bada boom, 11.183, which is exactly what we wanted it to be. That's the average that we got up above using the integral version. On the graph, though, let me bring the graph back up for a second. What we want to see is if we graph the 11.183, what we get is, well, first of all, we don't get much if I graph y equals this thing. That's not an average-looking thing at all, because that's not quite what we're doing here. This is the derivative graph, so we want to see this as a slope, and so I'm going to make it 1183x. Now, you'll notice that it is going to be an average right there, but if I turn on the derivative function, you'll see that it is exactly the slope from 0 to 30 of that graph, which is pretty cool. You can see it graphically on the derivative graph, matching up the exact average of what you want to see, which is pretty groovy. Okay. Anyway, that's cool. I just wanted to see it one more time. I'm trying to think. One more little trick I want to try. One more little thing before I move on to this problem. I want to try one more thing. I'm going to turn this back on here and see if it does anything. Did it do anything? Okay, anyway. All right. I'm over this problem. Let's move on to something different. Second monitor. Let's make you pick to the bottom. Here we are. Back to business. Okay. 5154. We're going to calculate the average value over in a given interval. And you may solve analytically or use a graphing calculator to solve. 154 is not too tough to do. It's relatively simple. We could probably do it right here in this space, but I am going to go over here. We are finding the average value of g of t, which equals 2t squared minus 3, on the interval from 0 to 4. Now, we've done a lot of this average value stuff. This is good practice for you to use this formula. It's really simple. It's a really simple formula. It's 1 over 4 minus 0 times the integral from 0 to 4 of 2t squared minus 3 dt. And this is easy enough to do by hand, so we can do this by hand. We'll use the calculator if we need to, but this is 1/4 times, let's see. The antiderivative of this would be 2t to the third over 3 minus 3t, and that would be evaluated from 4 to 0. So, let's leave the 1/4 out here in front. If we plug a 4 in, 4 to the third power is 64 over 3 minus 12. I'm just going to work this out as far as I can get it. This is 128 over 3 minus 12, man, which is minus 36 over 3. But at this point, I'm just going to grab the calculator and just chunk it out real quick. Let me bring my calculator cam back up to the front here. I'm just going to really quickly. Hey, what's 128 divided by 3 minus 12 divided by 4? Oops. Hey, 7 2/3. I like that answer. That works for me. Question B, very similar. This one we're definitely going to need the calculator for. It's this crazy function from 0 to 1. So 3e to the t plus natural log of t plus 1. And this is over the range from 0 to 1. Very similar problem. This is actually a lot easier. It looks more complicated, but it's much more simple because the range is from 0 to 1. So the fraction is 1 over 1 minus 0, which is just 1. And this is the integral from 0 to 1 of the function, 3e to the t plus the natural log of t plus 1. And you know what? We're just going to let the calculator handle that integral, honestly. Let's go up, open it up. Let's open up our fn int, 0 to 1. We have 3 times e to the x power plus the natural log of 1 plus x dx. Bam. And that's what we're looking for. 5.541 looks like it's about the answer. So we're good on this front. The next question is going to seem very difficult, but it's actually very, 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 very simple. But it's going to take a little bit of work for us to work through anyway. So 6155. Write the equation of the line tangent to the graph of this ridiculous function. It's not actually a function at all. At the point 0, 1. So let's get to it. We got a lot of work to do here. Now the good thing is they just gave us the point 0, 1. So when it comes to a problem like this, where can I have some room for this? How about 6155 right here? That's a highlighter. Our function is e to the xy minus the natural log of y equals 1. And we are doing this at the point 0, 1. We're looking for the equation for a tangent line at that point. Now, whenever we're doing an equation of a tangent line problem, it's a good idea to map out your or sorry, your point slope form from your Algebra 1 days. Maybe you remember it, maybe you don't. It's okay. We've been using it a lot this year. Now, the AP Calc version of this says it's y minus, f of a equals f prime of a times x minus a. Now, in this case, a is the number 0, and f of a is the number 1. So we're just going to make this problem a lot easier right off the bat by plugging those numbers in. But I'm also going to change f prime of a to dy dx, which you'll see in a moment why, x minus 0. Because the problem is, when it comes to the derivative portion of this problem, that's the one piece we're missing is the slope, which we can always find by taking the derivative and plugging in the point. However, the derivative of this function is going to be a little trickier to get because it's going to be an implicit derivative because we do not have a function in terms of y equals x. We're going to have to use a dy dx backwards way of solving it. So let's get to work. The first chunk, we have to take the derivative, d dx, of this entire thing. The first chunk is the e to the xy. The derivative of e to the xy is e to the xy. But we also need to multiply by the derivative of the inside part, which in this case is the xy, right there. And that's going to require the product rule, which is the original first thing times the derivative of the second thing, x times dy dx, plus the original second thing times the derivative of the first thing, which is 1 in this problem. The next chunk of the problem is the natural log of y, which has an easy enough derivative. It's minus 1 over y. But don't forget, since y is not the derivative's base, we're multiplying by dy dx. And this is all going to equal 0 because we are taking the derivative of 1 with respect to x, which is a constant. From here, as garbage as that looks, it's just a matter of solving for dy dx. Let's start by distributing the e to the xy power on this chunk there. We will have x times e to the xy times dy dx plus y times e to the xy minus 1 over y times dy dx. And now, if you're pretty good at moving things around using algebra, things get pretty simple from here. We're going to gather all the dy dx terms on one side and factor dy dx out of them. We're also going to move this y to the y times e to the xy power over here, where it becomes negative to the left side of the equation, or sorry, right side rather. And we're factoring the dy dx out of the other stuff. X times e to the xy minus 1 over y, like that. And now all we got to do is divide that stuff over, and we know that dy dx equals this ridiculous thing, which you don't need to panic about, and I'll tell you why after I'm done writing it down. I know it's bonkers, but don't forget, at the end of the day, we want to know what dy dx is when x is 0 and y is 1, which is really simple. Plugging in 0 and 1 for x and y is going to clean this thing up right away. We don't need to worry about any of that stuff because we're going to plug in easy numbers. In fact, this is going to devolve real fast into negative 1 over 1. I'll show you. First of all, it becomes negative 1 times e to the 0 power, which is 1, so that's negative 1 on top. This is also e to the 0 power, but that's a 0 in front also, so that's just 0. And then 1 over 1 is 1. I feel like I got a negative in there when I shouldn't have got a negative in there. Did I get a negative in there? Hang on, I'm just going to double check something real quick. Oh, it's a plus. This is my problem. This is what I do wrong, guys. I don't write the original problem down. It's a plus 1 over y. Whoopsie. Plus 1 over y right there. So this is a plus 1 over y, and this is a plus, and so it's 0 plus 1 down here. That's what I'm looking for, because I knew it had to be negative 1. This is negative 1 over 1, which is negative 1. So now that can go up here in place for dy dx. And so what we got is y minus 1 equals negative 1 times x. And that is it. Y minus 1 equals negative x. And you could even move that 1 over. Negative x plus 1 is the correct answer to the question. And you know what? Because we're here, and I have Desmos open anyway, what if I just got a new graph out? If I just a new blank graph? What if I typed in, here I'm just going to I'm just going to do this for fun. You can skip ahead of this if you want to, but I'm just indulging myself right now because I can. How about e to the xy power plus the natural log of y equals 1. There is the original graph. Pretty cool, right? There's 0, 1. There's the point right there. And what if I went over here and I just added on my problem? Y equals negative x plus 1. Ba-da-ba-ba-ba-ba-bam. I love a good tangent line, don't you? Isn't that just so satisfying to get that and get it right and check it out and know that you're correct? Isn't that cool? Okay, anyway, I'm not going to default. Okay. And I'm back on front. Let's see if we can get calculator cam up here, too. All right, I said I wasn't going to do 156, but I'm going to do it right now. It's not too hard to do. All we got to do really quick is check the f prime of 3, which is 3 squared minus 9 times g of 3. That's just going to be 0 times g of 3, which is 0. And f prime of negative 3, which is negative 3 squared minus 9 times g of negative 3, which is also 0 times g of negative 3, which is also 0. Both of these points are extrema. Whether that's all, honestly, you have to do. The only other thing is that g of x is always negative. Not that it matters. This just matters that the whole thing, honestly, it's always decreasing, I suppose. So, I don't know. That's all I have. It's negative. It's always negative. So, okay. Anyway, let's move on to 157. This is an easy one, too. Just a really quick, writing question. This is one of those nut problems where you got to write down the noun and the unit and the time. So, what we're saying here, c of 5 plus the integral from 5 to 31 of c prime of t is 25,000. That's all a big mouthful right there. That's all this big expression says. C is the calculator sales during the month of August, and t represents the day of the month. Now, so c of 5 in this case, this is how many calculators were sold on the 5th day. And this integral here is going to show you the change since then. So, in the context of the problem, write a complete description about what the integral is computing. Use correct units and be sure to mention the meaning of the bounds in your description. Now, I think there's a typo in the book here really quick, because they're saying that 25,000 calculators were sold from August 1st to August 31st. I don't think that was necessarily correct. But don't forget the NUT thing we got to write down. The number is 25,000. The unit is calculators, because this is the total number of calculators. I suppose C prime is probably the rate at which they were being sold, but C is going to be the calculators that are sold. So I would say 25,000 calculators were sold from August 5th to August 31st. And the reason why I think it's the 5th to the 31st is because the integral goes from 5 to 31, not from 1 to 31. So I think the book's answer is a filthy lie. I think it's got to be August 5th to August 31st. C of 5 is where we were at August 5th. So what's going on here is that C of 5 tells you how many calculators we've already sold, and then this is the change in the sales of calculators of that time. That's what we're saying. Okay, we have completed Chapter 6. Review tomorrow, test Wednesday, and we start Chapter 7 on Thursday because I'm a madman, and that's what I want to do. Y'all, I will see you guys in class. You guys are awesome. I'll see you in the next video, too.